we want to go to the zinc copper cell. Now we want to look at what is happening in the cell as we have discussed earlier. Now you will see that we have two beakers here. There's a beaker this side and there's a beaker on the other side. Inside these beakers we have what is called the electrolytes. So our electrolytes in this case will be zinc sulfate, and then our electrolyte this side will be copper sulfate. Now we have talked about the negative electrode. The negative electrode of a galvanic cell, we said that it represents the anode. So this will be our anode compartment. And the positive electrode, we have indicated earlier that it represents the cathode. So this electrode, because it's negative, is going to be our anode. And this electrode, because it's positive, is going to be our cathode. Now, we also remember that we said that at the anode, that's where oxidation occurs. At the anode, oxidation occurs, and at the cathode, reduction occurs. We need to remember that. As soon as we identify our anode as being the negative electrode, we should remember that that's where oxidation takes place. And as soon as we identify the positive electrode as the cathode, we should also remember that that's where reduction takes place. We should also remember that at the anode, that's where we find the reducing agent. The reducing agent at the anode, and at the cathode, we get the oxidizing agent. The oxidizing agent at the cathode. So that is what we have learned so far, and we want to now carry on with those lessons. Now, we want to look at the electron flow. We know that at the anode, that's where oxidation takes place, and because oxidation is the loss of electrons. Now, we know that zinc is now going to lose electrons, and those electrons which are lost from the zinc will move through the external circuit into the cathode. So in the external circuit, we have electrons moving from the anode to the cathode. In the external circuit, electrons are moving from the anode to the cathode. In the anode, that's where electrons are lost. In the cathode, that's where electrons are gained. Therefore, electrons move from the anode to the cathode in the external circuit. Now, the Sol bridge, it completes this circuit, and usually we put an ionic substance such as potassium chloride. The potassium chloride has ions. Since it's an ionic substance, it's going to split into ions such as the chloride ion and the potassium ion. What is the movement of ions in the internal circuit? The Sol bridge is the part which indicates the internal circuit. The negative ions, they migrate to the anode, while the positive ions migrate to the cathode. And this maintains electrical neutrality. So the function of a Sol bridge is to complete the circuit and also to maintain electrical neutrality. Now, if we go back to the standard reduction potential table, we will see that zinc has a greater reducing ability than copper. And therefore, zinc will undergo oxidation. So the zinc will undergo oxidation, and the oxidation half reaction is going to be copied from the table in reverse, where we start with the Zn that changes to Zn2 plus, and then 2 electrons are lost. And the copper is the one that will undergo reduction. So the copper 2 plus ions will gain 2 electrons, and that will form the copper solid. So this is the oxidation half reaction and this is the reduction half reaction. Now, the examiner will also ask you, identify the reducing agent. If you want to identify the reducing agent here and the oxidizing agent, we know that the reducing agent undergoes oxidation. The reducing agent undergoes oxidation. Therefore, our reducing agent in this example will be the zinc, because it's the one that will lose electrons. And then the oxidizing agent in this example will be the copper 2+ ions, which are the ones that are gaining electrons. Now, we continue with the explanation of the galvanic cell in the diagram that we have seen in the previous slide. We have seen that the zinc will lose 2 electrons to become Zn2+, which we wrote as Zn, losing 2 electrons to become Zn2+ plus 2 electrons. So that is the oxidation half reaction. This means that some of the zinc goes into the solution and it becomes oxidized to Zn2+ ions. Now, this will increase the concentration of the Zn2+ ions in the solution and make the solution to be more positive. It will make the solution to be more positive on the other side. The Zn2+ ions dissolve in a solution, causing the mass of zinc electrode to decrease. Remember, the zinc ions are being lost, therefore the mass of the zinc electrode is going to decrease, and electrons remain on the zinc plate, giving it the negative charge. So what we need to get from here is that the mass of the anode decreases as the cell continues to function, and the mass of the cathode will increase as the cell continues to function. At the cathode, we have seen the reaction, the half reaction that we wrote earlier there, that the copper ions gain 2 electrons to become the copper solid. The copper electrode will transfer electrons, and up until they reach the copper electrode will transfer electrons until they reach the solution. These copper 2+ ions inside the solution will gain 2 electrons. These are the 2 electrons that we are talking about. These electrons, where are they coming from? They are coming from the zinc electrode, which is decreasing in mass. Now, the copper ions are gaining 2 electrons. Therefore, it means that they are reduced to copper atom. This is the copper atom that we are talking about, which will then be deposited into the copper electrode. And because the ions are deposited into the copper electrode, the mass of the copper electrode is going to increase. So as the copper ions are changing into copper, these are the copper ions, they are changing into copper. The concentration of the positive ions, which is the copper ions, decrease. The electrolyte will now be more negative. So that's where the salt bridge comes in now. Remember, the charge of the anode is changing, and the charge of the cathode is also changing. The deposit of a copper atom to copper electrode will cause the mass of the copper electrode to increase, and the salt bridge will keep the balance between the decrease in ions and the decrease in ions, increase and decrease in ions. Now, in the zinc half cell, there is an increase in positive charges because of the release of electrons. Electrons are negatively charged. If electrons are released, then the positive charges is going to increase. In the copper half cell, there is a decrease in positive charge because electrons are gained. Remember, the copper 2 plus ions are positive, and as they gain electrons are negative. As they gain electrons, there will be a decrease in positive charge because electrons are gained. Then there will be a decrease in cell potential. That is, the EMF of the cell will decrease. And if this continues and continues, the V cell is going to decrease and decrease until it is zero. And that is where we say that the equilibrium has been reached and the cell is now dead. The zinc copper cell that we have talked about earlier. Now our ionic substance is sodium nitrate. We now see that remember the negative means anode and the positive means cathode. In the internal circuit, this is the salt bridge, it indicates the internal circuit. The positive ions migrate to the cathode always, and the negative ions migrate to the anode to balance the charges. Electrons in the external circuit, they move from the anode to the cathode. Remember, electrons are lost at the anode and they are gained at the cathode. So that is the movement that you need to understand. So if we look at the half reactions here, the zinc undergoes oxidation. We can see that with the increase in oxidation number, and also that the electrons are lost, and the copper undergoes reduction because of the gain of electrons. Now, when you have two half reactions, you can work out the net reaction from the two half reactions. The oxidation half reaction that we have here is the zinc changing phase to Zn2 plus with 2 electrons. Note that we use one arrow there, and we also have the copper ions gaining 2 electrons to form the copper, which is a solid. From these two, we can get the net reaction. Before we get the net reaction, we just need to make sure that the electrons are balanced, in a sense that the electrons lost in the oxidation half reaction are equal in number to the electrons gained in the reduction half reaction. In this case, we are very lucky that it's 2 electrons lost and it's 2 electrons gained. Therefore, the net reaction is the sum of the 2 reactions. We write what's on the left. On the left of both reactions, we add them up, and then we are going to add up what's on the right of the other reaction. Therefore, we will see in the net reaction here that zinc with oxidation number of 0 move to Zn2 plus with oxidation number of 2 plus, which shows an increase in oxidation number. So zinc undergoes oxidation, and the copper 2 plus with oxidation number of 2 plus moved from 2 plus to 0, which shows a decrease in oxidation number, and that is an indication of reduction. So the copper ions are undergoing reduction. If we were asked to write the cell notation for this reaction, remember when we write the cell notation, we start with the substance that undergoes oxidation, and then we come with the substance that undergoes reduction. Now, the substance that undergoes oxidation here is the zinc. And remember, the lines here indicates the phase change, and then the 2 lines here indicate the salt bridge. So when we write the cell notation, we are going to start with the substance that undergoes oxidation. And we know that zinc undergoes oxidation in this reaction. Therefore, we're going to write zinc solid, and which changes phase to become Zn2 plus in aqueous form. So this is the first part of the cell notation, and then we can check and see that the oxidation numbers are increasing. The Zn on the left has a 0 oxidation number, and the Zn on the right has a 2 plus. So this shows an increase in oxidation number. Now, on the right-hand side, we're going to write the substance that undergoes reduction, and as such, the oxidation numbers should decrease because that should indicate that this substance undergoes reduction. So for the reduction part, we are going to start with the copper 2 plus, which changes phase to become Cu. So this is solid. This one is aqueous. This one is aqueous, and the other one is solid. So that is just a reminder of how do we write the cell notation. You will also be aware that we are not using platinum in this case because both zinc and copper are metals. The salt bridge. The salt bridge in electrochemistry device is a device that is used to connect the oxidation and reduction half cells. That's why we say that the salt bridge completes the circuit. It connects the oxidation and reduction half cells in a way of completing the circuit. What are the functions of a salt bridge? It completes the circuit by connecting the electrolytes in the half cells. It allows ions to flow through without allowing the different solutions to mix. So the solutions will not mix because we have a salt bridge. And as the ions move, just remember that the negative ions migrate to the anode and the positive ions migrate to the cathode. And in moving these ions, it will help maintain electrical neutrality of the electrolytes in the half cells. So that is the salt bridge defined and its functions. The equilibrium or the dead cell. Now, as a cell is working and providing the flow of electrons in the circuit, we have seen earlier that as a cell is working, is providing electrons to flow in the circuit, there is going to be a change in concentration of ions in the anode and a change in concentration of ions in the cathode. Now, because of that change in concentration, the EMF becomes less, that is to say that the cell decreases. The cell delivers an electric current. We know that because of the electrons that are lost in the anode and gained in the cathode. And when a time when the potential is zero, so that is where the rate now, the cell has reached equilibrium, the rate of the forward reaction is now equal to the rate of the reverse reaction. As the cell starts functioning, the rate of the forward reaction decreases as the rate of the reverse reaction increases and increases up until a point where they are equal, and then with the cell will now reach the potential of zero when they are in equilibrium. The cell potential decreases as the concentration of the product ions increases. The product ions increases, and then the cell potential decreases because of that. The concentration of the reactant ions decreases up until equilibrium is reached, and that is where the cell potential is zero, and then we say that the cell is flat or is dead. The half reactions, we have the oxidation and the reduction half reactions, which are written as half reactions, as you have seen earlier. We use the standard reduction potentials to write the oxidation and reduction half reactions. We have seen them earlier. And the oxidation half reaction, we write it first, and the reduction half reaction, we write it below it. So that is what we do normally. The two reactions should be balanced, have the same number of electrons as indicated earlier, and then before we can get the overall reaction, which is the sum of the oxidation and reduction half reactions. The standard reduction potentials, again, just to remind you, we look at the arrows. We have the arrow pointing upwards, which indicates the increasing, reducing ability. So this means that any substance, the substances at the top have a greater reducing abilities than the substances below them. So this indicates that the substance that appears at the top of another substance on the table, the substance at the top undergoes oxidation and the substance at the bottom undergoes reduction. This is only applicable on the 4B table, and it will be applied in opposite when the 4A table is used. We can also use the E cell values. The E cell values, you will see that the substance at the top is more negative and than the substances below it. So if we take chromium and lithium, we'll see that the ECl value for lithium is more negative than the ECl value for chromium. So the more negative the ECl value, it means the greater the reducing ability. So a substance with a more negative value will more likely undergo oxidation than the substance with a less negative ECl value. The zinc copper half cells, let's look at them as we have seen in the diagram that was indicated earlier. The zinc oxidation half reaction, we saw it earlier, is written here, and then we can see that oxidation numbers are moving from 0 to 2 plus. This indicates that there's an increase in oxidation number. The increase in oxidation number indicates that oxidation is taking place. And we can also see that because of the loss of electrons. The Zn is the anode in the electrode. Remember that the anode will be negatively charged, and at the anode, that's where oxidation takes place. The half cell that takes place at the copper electrode, referring to the previous diagram, will be the copper one. And then we can see that the oxidation number is moving from 2 plus to 0. This indicates that there is a decrease in oxidation number, which indicates that the reduction is taking place. And when reduction is taking place, we know that that should be at the cathode, which is positive. So therefore, we say that copper is the cathode electrode. So we have, remember we said that normally we write the oxidation half reaction and the reduction half reaction below it. And then if we add them up, because the electrons are equal in this case, we get the zinc changing to zinc 2 plus, the copper 2 plus changing to copper, which are solids. And remember, just to remind you again, we can write the cell notation from this. The cell notation, we start with the substance that undergoes oxidation. In this case, it will be the Zn, solid, changing into Zn 2 plus. Look at the oxidation number increasing. And then for the other part, it would be Cu2 plus, changing into Cu. This is solid, this is aqueous. So that is how we're going to write the cell notation from the given net reaction. Remember that we can't use platinum as the inert electrode in this case because our substances are metals. Zinc is a metal and copper is also a metal. Now, the net reaction when the electrons in the oxidation half reaction and the reduction half reaction are not equal. Let's look at the oxidation half reaction for aluminium, where aluminium loses 3 electrons. So the oxidation number of aluminium here is 0. The oxidation number of aluminium on the right-hand side is 3 plus. This indicates the increase in oxidation number. Therefore, aluminium undergoes oxidation. Let's look at silver. Silver on the left, oxidation number is 1, and then silver on the right, oxidation number is 0. This indicates a decrease in oxidation number. Therefore, this substance undergoes reduction. This substance undergoes oxidation. Now, we want to get the net reaction. The oxidation half reaction has 3 electrons. The reduction half reaction has 1 electron. So 3 electrons are lost, but only 1 electron is gained. So the number of electrons they need to balance in the oxidation half reaction and the reduction half reaction. What can we do? we can simply multiply the reduction half reaction by 3. When we multiply, we do not multiply the electrons only, we multiply everything in that reaction. Therefore, that will be 3 Ag plus 3 electrons, which yields 3 Ag solid. Now, after doing this, the electrons are now equal. Then if the electrons are now equal, we can cancel them out. Then we'll have the the aluminum, and then the silver going there. That is what was on the left. And then on the right, we have this substance, the aluminum ions, and the silver going there. And this reaction is now balanced. Remember, always we need to practice how to write the cell notation. We have a Sol bridge, phase change. We always start with the substance that undergoes oxidation. In this case, the aluminum is undergoing oxidation. So that will be Al, and then it will change to Al3+. And our silver is the one that undergoes reduction, and that will be Ag+, and then it will change phase to Ag. This is solid. This is aqueous, and that is solid. So we need to be able to write the cell notation for all the reactions that we are given. And again, the platinum is not used in the cell notation or in the cell because aluminum and silver are both metals. The standard cell notation, the anode oxidation process always written on the left. We have seen that. The cathode reduction process always written on the right. The phases which are in contact are presented by a line. So we have shown that line, it indicates the phase change, and the double line indicates the salt bridge. So that is the cell notation for the zinc copper cell. Look at the zinc, oxidation number is 0. Oxidation number is 2+. Oxidation number is increasing. So this part indicates oxidation. Oxidation number is 2+. Oxidation number is 0. Oxidation numbers are decreasing. So therefore, this part indicates a reduction. Reduction occurs at the cathode, and oxidation occurs at the anode. The salt bridge is represented by 2 lines, which is very, very important there. So that was just a reminder of writing the cell notation as we have looked at it in a number of examples. Practice activity. Use the half reactions below to answer the questions. We have the half reaction here, and we also have another half reaction there. Now, when we are given 2 half reactions, like we are given in this example, we first need to check whether the substance undergoes oxidation or the substance undergoes reduction. So we have ion gaining 1 electron to become Fe2+. And then this side we have H+. It's also gaining 2 electrons and to form H2. Now, we need to use the standard reduction potential table to see which substance has a greater reducing ability than the other one, for us to determine which substance undergoes reduction and which substance undergoes oxidation. The questions are as follows. Write down the oxidation and reduction reactions. Identify the anode and cathode. Write down the balance overall reaction. Identify the reducing and oxidizing agent. Write down the cell notation. So firstly, we need to use the standard reduction potential table to see which substance has a greater reducing ability than the other. Now, let's look at them. We are given ion, 3+, and the hydrogen. So let's check in the standard reduction potential table. There we see the ion, and then we also see the hydrogen. So we will see that the ion has a greater reducing ability than the hydrogen. The ion has a greater reducing ability than the hydrogen, according to the standard reduction potential table. Therefore, we expect the ion to undergo oxidation and the hydrogen to undergo reduction. So if we answer the question in number 1, write down the oxidation and reduction half reactions, we are going to copy the reactions as they appear on the table. But remember that if you copy the oxidation half reaction, you do it in reverse. That is, Fe comes first, then followed by Fe 2 plus and 2 electrons. And the reduction half reaction is copied as it is, but with 1 arrow. So this is going to be 2H plus, gaining 2 electrons, forming hydrogen. So this is our oxidation half reaction, and this is our reduction half reaction. So that is how we are going to answer the first question. Now, the second question says, identify the anode and the cathode. Now, we will recall that oxidation occurs at the anode and reduction occurs at the cathode. Therefore, we can easily identify the anode as the ion, and then our cathode in this case, remember hydrogen is not a metal. We will need the inert electrode in this case, which is platinum. But the question says identify the anode and the cathode. Therefore, we can easily do that. Write down the balance overall reaction. To write down the overall balance reaction, we check the electrons. If the electrons are equal, we omit them. We add what's on the left, and we also add what's on the right. And then we need to identify the reducing and oxidizing agent. Remember that the reducing agent undergoes oxidation and the oxidizing agent undergoes reduction. And then you can easily find the reducing agent and the oxidizing agent. Then we can write down the cell notation. So that is how we are going to look at the problem as indicated there. So to answer those questions, I think we have written the oxidation and reduction half reactions. The anode is this is our anode in the ion, and then this one will be our cathode since the reduction occurs there. And then we're going to write down the overall reaction. If we write down the overall reaction, remember the electrons are now equal. We are now going to say ion, and then the 2H plus, which yields Fe2 plus, and the hydrogen. So that is our overall reaction. If we want to write the cell notation, in this case, remember the cell notation, if we want to write it, there's a salt bridge and there's a phase change. On the left, we write the substance that undergoes oxidation. On the right, we write the substance that undergoes reduction. The one that undergoes oxidation, in this case, we have ion, which is a solid that undergoes oxidation to form Fe2 plus, which is aqueous. And then the oxidation number is increasing, if you note there. Then we have the H plus, which is reduced to hydrogen. But remember, hydrogen is not a metal. Therefore, we are going to need the platinum as the inert electrode. Platinum will be needed as the inert electrode there. And this will be our cell notation. This is our cell notation for that reaction. So let's see if we've answered all the questions. The cell notation, we did identify it. Identify the reducing agent. Remember, the reducing agent is a substance that undergoes oxidation. The oxidizing agent is a substance that undergoes reduction. The balance overall reaction, we wrote it down there. So we have answered all those questions there. Now, EMF calculations. We need to be able to calculate the EMF, the cell potential of the cell in volts. Now, in your data sheet, you'll be given this part. You will see this part on your data sheet. Just before we use it, I just want to talk about it, how it can remind you of a number of concepts that we have talked about. The first formula says the E cell is equal to the E cathode minus E anode. The second one says E cell, this is the second one, E cell is equal to E reduction minus E oxidation. The third one says E cell is equal to E oxidizing agent minus E reducing agent. Now, this will remind you of a number of concepts. Now, you will see that at the cathode, that's where reduction occurs. Where reduction occurs, that's where you get your oxidizing agent. The anode, that's where oxidation occurs. Where there's oxidation, that's where you will get your reducing agent. You can use any of these formulas, but you can also use them to revise and remind yourself of the number of concepts. And how do you remind yourself? At the cathode, that's where reduction occurs, and that's where you find the oxidizing agent. The anode, that's where oxidation occurs, and that's where you find the reducing agent. So that is how we are going to calculate the EMF of a cell using the formula. You just choose one from the three, but just know that these formulas are there also to remind you what is happening at the cathode and what is happening at the anode. Where do you find the oxidizing agent and where do you find the reducing agent? The standard conditions. This cell that we are talking about, it works under standard conditions, and the standard conditions will be asked in the exam, and they are as follows. The temperature needs to be 25 degrees Celsius, which is equivalent to 298 kelvins. The pressure, it needs to be 101.3 kilopascals, and we are going to talk about pressure where gases are involved. This 101.3 kilopascals might be difficult for you to remember, but you can also say 180 M. So 101.3 kilopascals is equivalent to 180 M. The concentration, it needs to be 1 mole per decimeter cubed all the time. So these are the standard conditions in which the cell, the galvanic cell we're talking about, is operating on. The standard electrode potential. The standard hydrogen electrode. The standard hydrogen electrode, if we go back to the hydrogen electrode, you will see that the E cell value for the hydrogen is 0. Why is it 0? It is 0 because it is used as the reference electrode, which is used to measure the other electrode potential of all the other substances. So all the other substances' potential was measured with relative to the hydrogen, which was given the value of 0, meaning it is a reference electrode. Reference means the point from which we start to measure. So the standard hydrogen potential has a value of 0, and then it is a reference electrode where all the others were measured from. The pressure is 1 atmospheres, 180 M, or 101.3 kilopascals. The concentration, the standard concentration of 1 mole per decimeter cubed was used. The platinum, remember the platinum, hydrogen is not the metal. The platinum is used as the inert electrode. Platinum is used as the inert electrode to conduct the electricity or to allow the electrons to flow. And the temperature, remember, there's a standard temperature of 298 kelvins or 25 degrees Celsius. The standard hydrogen electrode is a redox electrode which forms the basis of a scale of oxidation reduction potentials. So we use it as a scale, as a reference, a point from which we start measuring. Its potential is 0, as we indicated, and then this is said to be 0 at all temperatures so that it can be used for comparison with other electrodes. It is used to compare with other electrodes, and then we use it to measure all the other potentials of the other elements. So this brings us to the end of our lesson. You are invited to join our next lesson, and there will be a homework that is given to you at the end. Thank you.